Hi, my name is Erik Thordsen, and in this presentation I will present our new approach for manifold embedding motivated supersampling, which is joint work with Erich Schubert. The goal of our supersampling technique is to improve local intrinsic dimensionality estimation. So before we take a look at how we are supersampling our data, let's at first recap what local intrinsic dimensionality estimation is. In the field of local idea estimation, we are generally assuming that our data lies on some lower dimensional manifold in our observed feature space. That means that our data lies in some locally Euclidean and possibly lower dimensional subspace. An observation we obtain from this is that all our data must adhere to some intrinsic features that form our parameter space. For example, if we are looking at images of cats, these intrinsic features might, for example, be the color of the fur, the shape of the cat's ears, and so on. In return, our observed features are then just images under some embedding function of these intrinsic features. We are further assuming that this embedding function is locally linear because in a finite data set, a sharp bend might always be approximated with a locally linear function with high curvature. The goal of local idea estimation is then to find the number of locally required parameters, that is, the number of our intrinsic features. The studies on local idea estimation can be separated into two major branches. The first one is expansion-based and investigates how volumes increase with a varying radius, or distance for that matter. The concept is quite simple, as for example, a ball volume increases in the power of the dimensionality. For estimators in this distance-based branch, the points in parameter space have to be mostly uniformly distributed. The other branch of local idea estimators focus on the geometry of the data. That is done by looking at, for example, pairwise angles in local neighborhoods and investigating which type of ball volume can possibly span such a geometry. As of now, both of these branches mostly ignore the complementary information. That is, distance-based estimators do not really use geometric information like angles, whereas angle-based estimators do not really make use of distance information. This is of course a bit exaggerated, as for example more recent distance-based estimators like ALIT or TLE indeed use distance information between neighbors, which in return gives somewhat of a trigonometric argument over angles. But for the most part, these information are not at the focus of the estimators. Distance as well as angular information, however, has specific advantages and disadvantages. The drawback of angular information is that it is not asemantically soundly defined in general metric spaces. Of course, we can compute a sort of angular measure in arbitrary metric spaces. However, its semantic interpretation is much more difficult than in Euclidean spaces. Distance information, in return, can be quite unreliable in smaller environments. If we look at the larger neighborhood on the right, we can see that the number of points in a given radius increases in the square of the radius, which is exactly what we would expect from a two-dimensional volume. If we, however, use a smaller neighborhood like the one below, we can see that the rough approximation displayed in the plot gives an estimated intrinsic dimensionality of 2.5, which is much larger than the ground truth. This simplified version to estimate the distance-based intrinsic dimensionality is of course not as profound as state-of-the-art estimators, but clearly highlights the drawbacks of distance information in small neighborhoods. If the main problem of distance-based intrinsic dimensionality estimation is the number of points in our environments, we could of course just increase the radius of our neighborhoods. However, both branches of intrinsic dimensionality estimation include a sort of locality assumption. That is, we have to guarantee that our considered neighborhoods are small enough to represent the local manifold structure. If we look at these circles on the right, only the smaller red circle on the right encloses a neighborhood that has clearly linear features, and thus only the smaller neighborhood on the right will lead to intrinsic dimensionality estimates that give the true intrinsic dimensionality for our one-dimensional manifold. To conclude, the core problem is that we don't have arbitrarily many points in arbitrarily small environments. But only because we don't have as many original points, it doesn't mean we can't have more points. That is why we propose to introduce supersampling to intrinsic dimensionality estimation by generating additional similar data points that lie on the same manifold or at least close enough to it. To do so, we use local covariances, which we claim are a good locally linear approximation of the manifold. The introduced spatial uncertainty by sampling additional points from local distributions adds distance information to angle-based intrinsic dimensionality estimation, as a radius of uncertainty for a faraway point has much smaller impact on angles than the same uncertainty for nearby points. Also, as local covariances are a geometric measure, this supersampling technique adds geometric information to distance-based idea estimation. Thus, we can enrich both approaches with complementary information. Additionally, the overlapping local distributions from which we sample additional points blur the overall data distribution for distance-based idea estimators, much like a Gaussian image filter blurs single spikes in the color distribution and pushes the data towards a uniform distribution. As a possibly interesting bonus, this supersampling technique can also be applied beyond idea estimation, for example in classification. Now that we have motivated why we intend to use supersampling in intrinsic dimensionality estimation, let us take a look at why we think that local covariances are a good choice for linear approximations of our embedding function. If we assume that our data lies on a locally linear manifold, then there has to be an embedding function that embeds our parameter space of the manifold into our feature space. We call this embedding function E. And if it is locally linear, we can also assume that a Jacobian exists. By propagation of error of linear operators, we then obtain that if we take an epsilon ball in parameter space and embedded it with our embedding function into feature space, the covariance matrix of this embedding has to be approximately proportional to the product of the Jacobian of our embedding function with itself. This, however, only holds for arbitrarily small neighborhoods. When working with real data, our neighborhoods are generally bigger than that. To accommodate for that, we get additional terms for noise and higher order derivatives of our embedding function, which we here hide inside a single symbol. Nonetheless, we argue that local covariances hence give a locally linear approximation of our manifold embedding function. This approximation is of course quite rough for very small k, as in these cases our neighborhoods are too small to give reliable covariance estimates. An improved technique to estimate these local covariances might be an interesting topic in the future. Now that we have explained why we want to use local covariances for supersampling, let us take a look at how exactly we intend to draw these samples. The most obvious choice to supersample points from local covariances would of course be the multivariate normal distribution. It is obviously faithful to our local covariances and also has very easy semantics in terms of uncertainty of our observations. Though the density of multivariate normal distributions is of course much larger near the center of the distribution. As we need a mostly uniform distribution in parameter space for distance-based intrinsic dimensionality estimation, this might introduce some problems. To obtain a uniform distribution in parameter space, we also try to sample uniform distributions from dipoles scaled with the Cholesky decomposition of the covariance matrix. In theory, this should provide us with uniform distributions in parameter space whenever the intrinsic dimensionality and the feature dimensionality are very similar. Sadly, this is typically not true for idea estimation applications. In an effort to obtain uniform distributions in parameter space, even when the intrinsic and feature dimensionality differ by a larger value, we try to sample uniform d-balls with an expansion rate fixed to some initial idea estimate. This should provide us with a truly uniform distribution in parameter space, however it requires some initial knowledge of the true intrinsic dimensionality, which we in general do not assume to have. As this is very similar to the second approach, a sufficiently close estimate of the intrinsic dimensionality however should suffice. All of these supersampling techniques however have some inherent problems. If we consider the distributions from which we draw samples as uncertainty on our original points, we can consider it as an additional noise term that is added to the already included noise in the data. From a purely distributional perspective, this should make our estimates worse instead of better. An additional problem is that any linear approximation is increasingly bad with rising curvature. If we look at this simple example, our point of interest is placed at a point with high curvature. If we take the nearest neighbors and compute a covariance matrix, here displayed as a unit circle of the Mahler-Nobis distance using this covariance matrix, we can see that it approximates the shape of the manifold already quite good. However, if we now draw samples from the multivariate normal distribution, we can see that the leftmost and rightmost points exceed the space occupied by our manifold. When repeating this process for all other original points, we end up with this very messy supersampling of our data. The enlarged neighborhood of our point of interest in the supersampling now introduces a much larger orthogonal component to the manifold and doesn't fit the manifold as good. But as always in life, it is probably okay to make a mess if you clean up after yourself. And that is why we propose to use a post-processing step in which we correct our samples to the manifold. The correction of our supersamples has some very simple goals. First of all, we want to stay in line with our generation method and hence make our points more aligned with the already obtained linear approximations. We can do that by scaling all our supersamples along the covariance matrices or derivations thereof that we obtained for similar points, that is, nearby points. Further, if some of our supersamples happen to be at the exact same location as our original points, which in theory could happen due to probabilistic sampling, then we want these points to stay unchanged because we just assume that our original points already populate our manifold, so we do not want to shift our original points off the manifold. We can do that by employing some sort of inverse distance weighting, which trivially gives a distance weight of infinite whenever a point is exactly matched. And at last we want to keep our density distribution mostly unchanged. That is, we assume to already have some sort of blurred out, mostly uniform distribution, and we do not want our data points to cluster at some location just because we are doing our correction. That can be achieved by, for example, rescaling distances to original points such that our correction is mostly a rotation around original points. With these goals in mind, our correction scheme works as follows. We start with generating some correction candidates, one per each nearby original sample. That is, for each supersample, we look at what original points are close by so that we can fit our supersample onto the linear approximations for these original points. As we want to employ an inverse distance weighting, we of course need more than one point over which we can compute a weighted mean, so we generate one correction candidate per original sample. These candidates then get rotated around our original points by multiplying with the covariance matrix or the Cholesky decomposition and afterwards rescaling to have the same Euclidean distance as the original supersample. This rotation step increases the plausibility of a given point for the local multivariate normal distribution approximately proportional to the square of the eigenvalues if we use the covariance matrix and linearly if we use the Cholesky decomposition. The details can be read up in our paper. Rescaling these rotated points to lie on a Euclidean sphere around our original points with the same radius as before, we can mostly keep our density distribution the same as before. Lastly, we take the weighted mean over all of our candidates and then obtain a corrected supersample. For these weights in the paper we added a few choices, which distance is used and whether or not we should use powers in the weighted mean computation. But for the sake of simplicity, in this talk we will only talk about the Mahler-Nobis distance. If we now consider the example from the last slide where we had this very messy supersampling of our dataset on this one-dimensional manifold, we can now apply our correction step. As you can see, the spread orthogonal to our manifold has drastically decreased. The mostly linear parts at the left and right end of our manifold have all but collapsed to single lines. The curved section at the top is also much more condensed and less scattered. If we now choose a new neighborhood from our corrected supersamples and again compute a covariance matrix, here again displayed as a unit circle of the Mahler-Nobis distance using this covariance matrix, we can see that the orthogonal component to the manifold is now much smaller. Also, our covariance matrix much better approximates the local structure of our manifold. To conclude, in this very simple example, our correction steps can largely improve the quality of our supersampling. Now that you have a rough overview over how our supersampling technique as well as the included correction steps work, let us take a look at experiments that we conducted. We performed experiments on many real and synthetic datasets. These synthetic datasets have the advantage that we have a ground truth ID estimate against which we can benchmark. Up in the top left you can see a Mobius band colored by Abbott estimates both without and with mass supersampling performed. As one can very easily see from these plots, the local ID variance is largely reduced when applying mass. Further, the geometrical structure of the Mobius band is much closer captured in the different Abbott estimates. The highly curved inner of the Mobius band has a higher ID estimate than the borders. This fits very well with our geometric interpretation of Abbott estimates and is further enforced by our mass supersampling. This improvement in quality, however, is not limited to angle-based ID estimation. As you can see from the histogram on the top right, the global variance of hill estimates is also largely reduced, giving a distribution which is much closer to the ground truth ID. Hence, in this experiment, the quality of both geometrical and expansion-based ID estimates can be improved with mass supersampling. In a different experiment, we evaluated the efficiency of mass supersampling on a 4-dimensional manifold embedded in 8 dimensions. As you can see in the top left, applying mass supersampling prior to evaluating local intrinsic dimensionality again improves results for both angle-based and distance-based estimators. As a reference supersampling technique, we also evaluated local intrinsic dimensionalities for the SMODE oversampling approach. SMODE computes linear interpolations to enrich a dataset, and as you can see from the plots, the ID estimates do not change at all or become worse. However, the mass supersampling technique has parameters that can affect its performance. On the right side, you can see the median ID estimate given different parameterizations of the mass supersampling technique. For small neighborhood sizes for the initial covariance estimation, the median ID estimate can be either too low or too high, depending on the size of the neighborhood. In our experiments, we observed that the optimal neighborhood size is roughly around the minimal normalized ID estimate variance, at which point the median ID estimate is also closest to the ground truth ID. For improving the ID estimation quality, it is thus probably useful to compute ID estimates for varying parameters and choose the parameterization that works best. When using the mass supersampling technique for other applications like classification, it is probably not as important to find the proper neighborhood size. To conclude, we have introduced the mass approach, which is a manifold-aware supersampling technique. Aside from giving a theoretical motivation, we have shown how it can in practice improve ID estimation due to the complementary information introduced to both distance and angle-based estimators. By doing so, we can reduce the neighborhood sizes required in ID estimation, which in return improves on the locality assumption and thus strengthens the ID estimate quality. Using local covariances as a linear approximation technique has further been exploited in our recent work called CANDLE, which is a classification approach which we proposed at the LWDA 2021. Using such an implicit manifold model can probably also be applied to other problems as well. Lastly, our mass supersampling technique can also be used in use cases beyond ID estimation, such as classification, where, for example, the SMODE oversampling technique has been successfully employed before. Although our preliminary experiments in that regard show to be quite promising, this is not sufficiently explored yet. I hope you enjoyed this presentation, and I'm looking forward to have nice discussions with you at the conference.